Hi, I'm Francesco Del Buono and I'm presenting automated machine learning for entity matching task. Entity matching refers to the problem of determining whether two data entries refer to the same real-world entity. In other words, given a pair of textual descriptions, if the matching schema are plain, we need to establish if they refer to the same real entity. Despite the effort put by the research community, entity matching is still an open challenge, and state-of-the-art entity matching tools are based on neural network. Besides this system address effectively the problem, they require a significant amount of label data for their training, specific skill in modifying, training, and configuring complex neural architecture for new scenarios. Our goal is to design an entity matching architecture that is accessible also to non-expert users, enables users with limited expertise to train high-quality models, and able to generate low-cost baseline for entity matching tasks. A possible solution can be the implementation of automated machine learning systems, also called AutoML. But what is AutoML? AutoML is a recent research topic and consists in the automatic identification of the most effective algorithms to make machine learning inference requiring minimal human intervention. HTML could be defined as a combined algorithm selection and hyperparameter optimization problem. For example, AutoScape combines a meta-learning technique to boost a Bayesian optimization with an ensemble method applied to the model selected in the previous step. Instead, AutoGluon uses ensembling multi-layer stacking techniques to combine multiple models. Therefore, AutoML can make the application of entity matching technique possible also to less experienced users that are able to train high-quality models. In addition, introducing some form of automation will reduce the cost and time for the model deployment. Despite this, there are two main problems with current AutoML solutions. First, they are ineffective in dealing with the peculiarities of entity matching, where each record is a description of pair of entities. Second, they have poor pre-processing technique for solving NLP tasks. How can we solve these two problems? The design of the solution was based on a preliminary analysis of the main features implemented in the existing approaches. This allows us to get insight into the design choice to adopt in the creation of the architecture. First, we need to pre-process sequential data and keep in mind the pair record structure. Second, external knowledge base can be effectively exploited in machine learning architecture, addressing entity matching tasks to reduce the need for annotated data. Third, pre-training transformer architecture are able to learn the semantics of word better than conventional word embedding techniques. Thus, they could serialize numerical vector the field of the entity matching dataset. After taking into consideration the previous insights, the proposed architecture is based on two main steps. First, the preprocessing, that is called the entity matching adapter, with tokenizer embedded and combined. Second, the model, that is based on AutoML. We explored and used in particular AutoScape, AutoGluon, and H2O AutoML. Moreover, we consider AutoML systems as black box tools, and they have been experimented with their default configuration. No parameter tuning has been performed. Now we focus attention on entity matching adapter component that is based on three steps. The first step, the tokenizer, transforms an entity pair into one or more token sequence. This component defines how to combine the value of the records to obtain tokens that enable the automatic learning of deep relations between attributes describing the same feature of different entities. There are three alternative ways for performing this operation: the unstructured, attribute-based, and hybrid tokenization mode. The second step, the embedder, encodes a token sequence in a multidimensional vector. In particular, we decided to use pre-trained transformer-based architecture like Bert, Distelbert, Albert, and Roberta. The third step, the combiner, summarizes the embedding for each entry in a single multidimensional vector. The standard approach experimented in the paper for performing this task is to calculate an average embedding. After the explanation of the concept of the idea and the architecture of our solution, we need to measure the effectiveness in solving the entity matching problem. Therefore, the evaluation is performed on 12 Magellan datasets, which belong to three categories: structured, dirty, and textual, representing different dataset characteristics. In addition, the following evaluation aims to provide an experiment answer to three main questions. First, how effective are standard UTML systems in solving entity matching tasks? Second, to which extent the performance of UTML system applied to the entity matching task benefit from data preprocessing techniques? Third, how much UTML system pipelined with entity matching adapter outperform the current state of the art in entity matching? In this first evaluation, we evaluate only the AutoML system in solving the entity matching task. And we can see that AutoML systems are not effective in solving the entity matching as the matcher. In addition, the autoscapular system requires the application of a data preprocessing step to transform categorical features. And we perform this operation via standard word-to-back embedding, where the average embedding for each token of a non-numeric attribute has been computed and concatenated. Thus, there is no optimal system that clearly outperforms the other. In this case, we have an average F1 score of 48% for AutoGluon, 51% for H2O AutoML, and 52% for AutoScapular. Next, in this second case, we evaluate to which extent the performance of AutoML system applied to entity matching tasks benefit from data preprocessing techniques. We can see that the entity matching adapter largely improves the effectiveness of AutoML in addressing entity matching tasks. In particular, the entity matching adapter implementing hybrid tokenizer typically obtains the best performance, and the Albert embedder achieves the best results. The average F1 score increase of 28% for AutoGluon, 23% for H2O AutoML, and 24% for AutoScapular. Finally, we evaluate how much AutoML system pipelined with entity matching adapter outperform the current state-of-the-art model, DeepMatcher. In this evaluation, our solution performed also greater than the state-of-the-art entity matching tool. AutoML system limited to 1 hour of training show better effectiveness than DeepMatcher in 5 out of 12 datasets. Thus, if we consider a tolerance threshold of 12%, our systems are comparable or outperform DeepMatcher in 9 on 12 datasets. Moreover, if we limit the training time at 6 hours, our systems are comparable or outperform DeepMatcher in 11 datasets. In conclusion, the adoption of AutoML system will make machine learning and deep learning based approaches for addressing entity matching tasks usable also for non-expert people. Our experiment showed the introduction of entity matching adapter achieves a performance similar to the one of entity matching task specific system, but it doesn't require expert user to tune it. In the future work, we try to improve the performance in two ways. First, introducing a data augmentation technique for creating more balanced training dataset for the AutoML system. Second, by experimenting techniques for improving the embeddings. Thank you for the attention.